Hello there, today we'll be doing sliding window maximum. In this particular problem, we are going to be given a array of numbers, and in this array, we're going to be given a sliding window immediately. And in this sliding window, we must find the largest number in the window. In this case, the window size is 3, and the largest number is 3. And then we shift the window over, and we find 3 again. So we have a maximum of 3, and 5, and 5, and then 6, and then 7. Of course, as you can see, the runtime for this operation immediately is O of n for numbers in the numbers array, and we need to check the size of the window, so times k. So it's O of n times k. Of course, it's O of n minus k, but who's talking here? So, what we can do is bring this speed down to O of n. And you might ask, how are we going to get away from the max function? Well, that requires a data structure. And the data structure that we will need here is one that is a array that we can remove items from both sides. So we want the index and the value here. And if the value is of the new item is greater, then we'll replace the value. If the index is larger than the smallest index, then we'll replace the index. And that way, we can keep the oldest yet biggest item number value in our data structure. Yes, when you encounter this type of problem, immediately think, oh, we need a different data structure, and this data structure should do these two things. It should keep the index and the biggest value. These are two pieces of information that we need to maintain to find our answer at each particular moving window. And how are we? Let's check this out. Let's see how this is done. So once we have these two biggest pieces of information, let's start with L and R here, and let's grab 0, 1, 2, 3, 4, 5, 6, and 7. And let's see what happens at the first item. The first item, we throw this in, 0 and 1. Not too bad, very easy. And in the second item, we throw in, well, 1 and 3. When we see 1 and 3, we see that 1 is smaller, so we remove it. And now the biggest item is in the 0th place. Great. And as you can see here, the 2, we keep that because it's smaller. There's no problem in that, and we might need it in the future. And once we hit this particular point, we can start generating our results. So first thing is 3, we got. Then we move left we're moving the left now as well as moving the right. And we see a -3. Fine, we put that in. Great. As you can see, we can now put the second item in, 3. Now, as we move the left and right corner forward, we notice that the next item is going to be, was it 5, I believe? It's a 5. So we put the 5 in, and what happens when we put in the 5 is that the 5 is greater than -3. We put that in. The 5 is greater than -1. Yes, we put that in. The 5 is greater than 3. Yes, we put it in. So 4 and 5, that's the biggest item, and we just automatically put this in. As you can see, the size, the last item is not greater than our index, so no problem there. Then we move to the next item, 6 and 6. So we remove it, and we have 6 and 6. Then we throw in the 6 in, and then we go to the next item, and we throw in the 7. Of course, we replace these because 7 is bigger. And all done. We have our answer. And this way, we are able, well, I think we missed the 5 there somehow. Maybe somewhere in there. I don't remember. I think at 3 we missed. Okay, anyways. Right. So what happened here was that we were able to do this in O of n time because we had the pieces of information readily available to us. By keeping our biggest value as well as the index. So yeah, this is great. This is combining multiple ideas. One, the data structure, an array, and 2, combining it with a sliding window. So I think you need to have a pretty good understanding of both to be able to do this problem. And this also coincides with the double pointer items, 2-pointer systems that is required to do sliding window pretty well, but the pointing system is a little different. Anyways, let's get to the problem. So, in this particular problem, we have results, empty array that we have to fill in. We have a left pointer that we set at 0. We have a array that a cache, let's just say, and let's do a DQ because we have to remove items from both sides. And I think we're ready. So for our in range, length of nums. So we're gonna go through every single item and let's talk about adding items. So in order to add an item, we must make sure that this item is going to be, if it's bigger, we need to remove the smaller items. So our cache, we need to make sure that we're going to do an index to value at each particular spot. So this is how we get our latest number or latest value. Let's just say value. And I think number is better. So if our new num, add num, is let's say greater than the latest number, what happens is that we need to remove it, greater than or equal to. Yes, so let's remove it. So pop. Great. And then once this is all done, otherwise, break, and let's add this number to our cache. So if, let's say our left side is greater than our, okay, so what's next? Let's think about what do we have here. We appended our R. That means our window has grown. That means we need to make sure that our window size is of the correct length. So earliest index currently earliest index is cache at 0, 0, and if earliest index is less than the left, then we need to remove that. So cache.pop left. And if, let's say, our window size is greater or equal to k, that means we need to get our largest number, which is equal to cache at 0 and 1. And we need to append that number to our results. Then we do a L plus equals 1 whenever our window size has hit its limit. With that, we can return the results. All right, wonderful. And let's submit. Okay, not too bad. Right. So how can we make this better? We talked about our window size. We talked about earliest index. Our story that we're telling here is that we have indexes on both sides. I'm not sure what we can do to make this even better. So I don't think it's clear in this particular problem that we're using a brand new our own data structure to make sure that we are within bounds, that we are removing the earliest index and also getting our biggest number. I think we need some more information. So cache holds the largest number in 0 index at 0 index. And earliest index at 0 index. Okay, I think that's all for this problem. The problem is that can we remember with this code when we read it next time and read it immediately, whether we can see that, oh, we are creating our own data structure so that we can get our largest item. And this data structure, what it does is that it stores the largest number that we can possibly have, and it also stores the earliest index. I think this helps a lot, the earliest index, and we look at the latest number and add number, right? So I think the largest number part is what we're missing. So I think we can say store largest number at index 0, and let's keep all this together. Remove earliest index outside of of window size, and get largest number within window size. I think that those comments help a lot. Next time we read this code, I think the problem helps a lot. And maybe we can talk about the function itself. Return the list of max items within sliding window of size k for list of nums. I think with this is pretty clear. I think this is pretty good. We're not dealing with these weird caches, we're dealing with words instead, and largest nums and everything. And I think that's very helpful. I think next time we read it. I think that should be all for this problem. If you enjoyed this video, like and subscribe. If you want more, check the link in the description below. Thank you very much, and I'll see you in the next one.